So bad. No. Going to the meeting. Am I going? I don't know. So I didn't. Yeah, you need points. How many points do you really think? Perfect. Oh, yeah. Can you mark me presents for the first two meetings? Because I probably like. Okay, bye. Wait, no.
As long as she's not.
I'll do it.
Bye, guys. Let's start. Hey, page 16. Okay, so we have natural log of x minus 2. That's the curve here. Oh, the minus 2 is outside of natural log, so it's natural log of x, and then separately minus 2. So it's not a parentheses x minus 2. So it's this. And g of x minus 4 is the linear graph here. Okay, so we start off with the easier problem with horizontal axis of revolution, which means you're going to be able to deal with vertical radius, which means you can keep the functions that's provided for you. These are difficult intersections to solve by hand, so we're going to make the calculator do it for us. We can graph the two functions and look for the intersections, and the x value intersections will be the bounds for your interval. Oh, I want to point something out here. Sometimes students feel like the axis of revolution, if it's really far away, that it's going to impact the bounds somehow. The bounds are just for your shader region. It doesn't matter where your axis of revolution is. Your bounds is just meant for your shader region. If you do zoom box, you can zoom in on that region a little bit more closely so that it'll be easier to maybe look for intersections. Okay, second trace, intersect. Pick points close to the intersection, make the calculator find it for you. You'll get 3.146. And the other one will end up being 0.159. Okay, so from your, well, first off, we know that even though we do have a flat surface, it's not a horizontal or vertical flat surface. So no matter where you put your axis of revolution, this is always going to be a washer method. So this is even more obvious since there's a gap. It's not even touching the graph here. But from the axis, we can extend to the furthest boundary. That's going to be your big radius. And then again, from your axis, extend to the closer boundary. And that's going to be your little radius. Again, make sure that we remember that the dotted line is the new center of the graph. And this is going to end up rotating around. It's going to look like a weird kind of ring-shaped object. But we never want to connect between the two boundaries and call that the radius. Okay, it's got to involve the dotted line in order to call it the radius. Okay, so now let's build our big radius, big R and little r. Big radius is 2 minus parentheses x minus 4. Little radius, 2 minus parentheses natural log of x minus 2. It's always good to protect the lower function with a set of parentheses. Otherwise, we may forget to distribute the negative through. Okay, we're ready for our volume formula, pi integral big radius squared minus little radius squared. Make sure that each of your radius is getting squared separately. We don't want to be merging them together and doing the squared once. Got to show up twice. Okay, the rest can go in your calculator. This wasn't able to convert to a fraction for me, so I just did 3 decimal places, add pi at the end. Okay, so this is the easier of this wash method problems because we don't have to change anything with our equations. We can keep them the way they are. But for part B, we're rotating around a vertical line x equals -1. So we know that anytime we have a vertical axis, we're forced into a horizontal radius. If we're forced into a horizontal radius, we know the equations need to be put into a form that we can use. It has to be rewritten. You have to be able to solve for x. Right? But so from the axis all the way to the diagonal line is going to be your big radius. We call it big R of y. And then from dotted line to the closer, which is your curve, that's going to be your little r. Right, so we have to rewrite these equations. Initially, this was y equals x minus 4. And let's just get that x on this left side and solve for x. And the y equals natural log of x minus 2. I need to solve for x. So add 2 to both sides. Okay, how can I get x by itself if I have natural log?
Raise it.
Yeah, raise it. E is the base. Right, so every equation that we're going to use to build our radius has the form that we need. X equals -1, x equals 4 plus y, x equals e to the y plus 2. I should have written the order pair down because now we're going to use those y values at these order pairs. So those y values ends up being negative 3.8 and negative 0.853. Okay, so here are our big R and little r. Big R, right minus left. The right endpoint is sitting on the pink highlighted graph, linear graph, which is the 4 plus y. Minus the left endpoint. The left endpoint is sitting on the dotted line, which is x equals negative 1. Careful, we got to keep track of the multiple negatives here. So minus a negative 1. And a small radius, right minus left. The right endpoint of my little radius is sitting on the curve. The curve has been adjusted to be represented as x equals e to the y plus 2. So e to the y plus 2 minus a negative 1 as well. Okay, integral from your lower y value to your higher y value. Big radius squared minus little radius squared. On paper, you're writing y variables down, but in your calculator, you're going to type in x's. Okay. Any questions? All right, try number 4. So x squared plus 2, that's the parabola. Horizontal line y equals 2, and x equals 0, x equals 4. So you're always going to be told where the boundaries are, and then you can use the boundaries to help you make sure that you're looking at the correct shaded region. All right, so vertical axis, we're going to have to draw horizontal radius, and we see there's a gap. So we know that there's going to be a hole that needs to be subtracted out, and we need to build out our 2 radius, one that's going to extend from the dotted line to the furthest boundary away from the shader from the dotted line, and then from the dotted line to the closer of the 2 boundaries. Right, every equation needs to be looking like x equals before we can use it. Well, this vertical line is already x equals 4, so that we know we can use that. But this equation, y equals x squared plus 2, is good for top minus bottom, but it's not good for right minus left. So let's spend some time to solve for x. we get plus or minus square root, but we're going to only take the positive square root since this square root is, this equation is on the positive side instead of the negative side. So it's going to be on in the first quadrant. So positive square root of y minus 2. Okay, your bounds is from lowest to highest y value. So lowest y value can clearly tell is going to be 2. The highest y value is going to be wherever this curve is at 4, right? So we can just plug 4 into this function and find the y value at that point. Right? Find the order pair at this point. So we know the x value is 4, plug 4 into the curve, and you're going to get 4 squared plus 2, which is 8. So you're just looking for the y value. You're not going to be able to find the intersection of a vertical line and the curve. I think it's just easier to just plug it directly into the function and find that y value. You don't have to do any calculations with your with intersecting feature. Just find that y value there. Okay, so bound will be from 2 to 18, but let's build our 2 radius. We know this is washer method. Okay, right minus left. So right endpoint is sitting at the 5. Left endpoint is sitting at the root y minus 2. And then right minus left. Right endpoint at the 5. Left endpoint at the 4. So 5 minus 4. Square your individual radius separately. Right, we're on page 16. Okay, part B, same shaded region. But now we're rotating about the line x equals 4. Now, what's this here? Yeah, this is this method. Okay, so I want us to be able to see that distinction between disk and washer. If your dotted line is up against a flat surface and you don't see any gaps at all, then you know it's going to be this method. All you need is 1 radius. So we can reuse a lot of information from part A, same bounds, same equations, but all we need is 1 radius. So 4 minus root y minus 2. Okay, any questions with Washer method. Okay, we only have one more topic to cover, and we'll cover that today. We'll finish it up, and then we can begin our quiz review tomorrow. Your quiz will be next Thursday. It'll just be over area, disk method, washer method, cross section. Okay. So we can begin our quiz review tomorrow. So we'll have Thursday, Friday, Monday, and Tuesday. But okay, so Wednesday is going to be senior service day. So Thursday is your quiz. But I'm not going to use all of the class periods next week to do quiz review. We'll still use second half of class, but I want to start going into AB review, some FRQ reviews for quizzes that we're going to be taking after the break. Okay. So, but I will have help sessions for area volume Friday and Tuesday. Okay, so Friday morning and Tuesday morning. And I'll give you your quiz review packet tomorrow. All right, so page 17. So cross-section is the shape that results if we were to cut the object in half and look at the resulting shape. So this method and washer method, both of them have this rotation, this rotating concept involved, right? And that rotation is always going to create circular shapes. And so for this method, if we were to cut the objects in half and open it up, we're going to see circular discs. Okay, or sorry, circular, just a circle shape. For washer method, if you were to cut the object in half and open it up, you're going to get circular rings. So both this method and washer method have circular cross sections, right? But now, what if we wanted to have volumes of objects, or what if we're talking about objects that have different cross sections? What if we open it up, that shape is no longer a circle? What if that cross section is a square or a rectangle or a triangle? And they're going to end up looking like these odd shaped objects that we don't really have names for. But we really don't have to worry about drawing the shapes. We just have to be able to identify the formula and then plug into the calculator. Okay, so let's look at this particular instance here. So let's say we have a shaded region, okay, and right now it's drawn in a three-dimensional way, but we're going to just use a normal two-dimensional coordinate plane. But right now, you can tell that this region is basically the same as if we're drawing the quadrant with a quarter circle here. But let's say we wanted to build squares on top of this base. Okay, so we're no longer rotating. We're now building these different shapes that's going to extend from one boundary to the other. So let's say we want to build squares. So if we want to build squares, then we can see that these are all differently sized squares with all different heights and different bases. And eventually it's going to end up looking like this, right? So this object, whatever this object is, if we were to cut it in half, if you were to open it up, you're going to get differently sized squares as your cross section. Okay. So we're going to be building these volumes of these objects. And we just have to be able to follow the instructions in terms of how they want us to build it, and also what shapes to build out of it. So it may be asking for a square. It may be asking to build different sized triangles, rectangles, or semicircle. Right? So they're all going to be a very similar formula, just some adjustments with the cross section. Okay, so for example one, we're just going to be working on this particular problem. Okay, we're going to be building the cross-section volume of this cross-section. So example one, find the volume of the solid of the base bounded by the curve y equals square root of 1 minus x squared. So we have square root of 1 minus x squared. That's just, if you put it in the calculator, it's going to end up being a quarter circle. So we have the quarter circle, we have x equals 0, we have y equals 0. So it's basically just a two-dimensional version of this, this orientation with a three-dimensional shape. Okay, we want to build squares that are parallel to the y-axis. So which direction is that? Parallel to the y-axis. Vertical, okay. So you're going to be building vertical lengths that's going to extend from one boundary to the other. So we're going to draw it this way. Now for cross sections, there is no axis of revolution, there is no rotation, and you're always just going to be connecting between the two boundaries, okay? Just like how you do with area. Right? So in this case, it's going to be a vertical length, and I'm going to call it a base length. Right? And that base length is what we're going to be using to as one of the sides to build whatever shape we want to build, either a triangle, a rectangle, a semicircle. So your base length, it's just going to be, in this case, top minus bottom. If you see a vertical base, it'll just be the same way that you do it with a vertical rectangle. You know it's going to be an easier setup because you don't have to do any adjustment with your equation. But anytime you see a vertical rectangle or vertical base or vertical, if you see a horizontal base, a horizontal rectangle, or a horizontal radius, you know that your equations need some adjustment to be rewritten. Okay, so the top of my base length is sitting on the root 1 minus x squared. The bottom is sitting on the y equals 0. And we're just going to set up that length just like how we would if it was a previous section. So root 1 minus x squared minus 0. Which we can drop to 0 because we know that's not going to change anything. Now that we have the base length, we're going to find the appropriate formula that we want to build. In this case, we want to build squares. So we're going to find the area for a square and get it out of that. So we're just kind of building it one piece at a time. We're starting with a one-dimensional information, and then we're getting to the two-dimensional information with area. This is just a square, so just base square, basically length times height, with length and height being the same. So in this case, my base squared is just root 1 minus x squared. And then once we have the two-dimensional information, we're going to give it that third dimension. And that third dimension is just putting an integral around to give it that third dimension. So right now we have area, and then we put the integral around it, and it gives it that third dimension. We're basically accumulating all these individual squares from one end of the boundary to the other. So our volume is just the integral of our area and because everything's in terms of x, our bounds is also in terms of x. The furthest left is 0, and the furthest right, if we were to look for the x-intercept, that ends up being x equals 1. Okay, there is no pi involved because there is no rotation, there is no circle related object here. So it's just integral of square root minus x squared, which we can drop the square root and square because they cancel out. And then we can just enter that in your calculator. You're going to get 2/3, and it's still a volume calculation, so units cubed. So you're always going to be told how to draw your base length, either vertical or horizontal. And then we just have to think about, the way that they're phrasing it. It could be parallel or perpendicular to the X or the Y axis. So there's 4 different ways that they can say either vertical or horizontal. We just have to kind of pay attention to those words and that, that we're carefully looking at these words and how they're describing it before we conclude whether it's vertical or horizontal. Okay, let's go to next page. Again, we don't have to worry about what the object looks like. We're just gathering enough information, plugging into the formula, and getting the volume. All right, number 2, find the volume of the solid. We have y equals x squared and y equals 4. So that's going to be a parabola in the horizontal line. Cross sections are now isosceles right triangle with hypotenuse on the base. So there's a formula for that. And it's a cross section. So we want the cross section base to be parallel to the x-axis. Okay, so think about the combination of these 2 words here. Parallel to the x-axis. Which direction is this? Horizontal, right? X-axis is horizontal. Parallel to it, we're going to keep that same horizontal. Okay. So you're going to just extend. There's no more axis of revolution. You're just going to connect from one boundary to the other of your shaded region. Now we need to get our equation in the proper form. So there's only one equation, but this is going to turn into 2 in a second. So if I solve for x, this is y equals x squared, or same thing as x squared equals y. If I solve for x, I get plus or minus square root of y. So this is where the 2 equations are going to come into play. We have the positive square root, which is in the first quadrant, and then we have the negative square root, which is in the second quadrant. So this side is x equals root y. And then the other side here is x equals negative root y. Our bounds, we're stacking these triangles from the lowest y value to the highest y value. Okay, and so the idea is that we're just imagining these triangles are going to come out of the page. Okay, so again, we don't have to worry about what they look like, but essentially this is where all these different size triangles are sitting on top of the base, and they're just extending from one side to the other. Okay, so imagining triangles are coming out of the page. So the lowest y value is 0. The highest y value is 4. In this case, it's easy to spot. Other times you may have to use your calculator to find intersections, but in this case, we can obviously tell where the y values are. And then if we want to do right minus left, we know everything's in terms of y, our equations in terms of y as well. So we're going to build it 1 dimension at a time. So we start with our first dimension is just getting that right minus left, getting that base length. So right endpoint is sitting on the root y, left endpoint is sitting on the negative root y. So root y minus negative root y, which ends up being what? Yeah, 2 root y. Okay, so 1 dimension at a time, we have our one-dimensional base length. Next up, we're moving to our area. So our area is 1/4 base squared. So just put the base that you found into the formula. And then give it that 3rd dimension with the integral. And then we're extending this from 0 to 4. no pi involved since there's no circle shape here. You can clean this up first and then put in the calculator or put it directly into your calculator. But here I see the 1/4 and 2 squared will be 4. It's really just this here if you want to make it simpler, but either way, you're going to get 8. And no, we don't attach pi here since there's no circle. I know that the base kind of looks like a circle shape, but we're talking about the shape that we're building. We're building triangles here. And the triangle, which is not shown here, is what's used for your formula. Okay, example 3, same shaded region. But now we're building semicircles. Semicircle has a formula adapted as well. But look at the direction here. It says perpendicular to the y-axis. Okay, which direction is that? Still horizontal. So I want to point out that there are different ways that it can describe horizontal, and there's also different ways they can describe vertical. So you just have to pay attention to the combination of these words here. Y-axis starts off vertical, perpendicular to it, it's going to make it horizontal. So that's good in the sense that essentially we can reuse everything here, right? It's going to be the same base length, same bounds, just a different area. Now we do have circle related information here. So imagine semicircles are coming out of the page. So this is the only time with cross section that you're going to have pi involved, because this is the only thing here that's circle related. Everything else is not circle related. But it's circle related not because of the fact that there's rotation, but because we're building something that's circle related out of the page. And I like to do what I do with previous disk and washer method is hold on to that pi. Don't put it in the calculator, put everything else in the calculator. Okay, so with what we know, see if we can try example 4. We may need to use our calculator to find the intersection. I'm going to zoom in on that region so I can have an easier time finding the intersections between the graphs. So we're doing perpendicular to the x-axis. Which direction is that? Vertical. All right, so vertical, we know that's going to be an easier setup. Our bounds is in terms of x. Our function we can keep. Moving on to our two-dimensional information. We want an isosceles right triangle with a leg on the base. That's going to be 1/2 base squared. And again, there's no rotation here. There is no air, there's no circle related information, so there's no pi involved. We just plug all this in the calculator. Oops. My bad, 0.464, not 0.613. That's the answer. 0.464. Now we do have to work on memorizing these formulas. I know it looks intimidating here, but look at these formulas for a second. What do you see as similar between all these formulas, or most of these formulas? Yeah, they're all are just base squared. The only thing you have to worry about is getting that coefficient correct. So, square is just base squared, no coefficient. So it's either 1/2 for leg on triangle, 1/4 for hypotenuse on triangle, √3/4 for equilateral triangle, and pi/8 for semicircle. And rectangle is just base times height. So, but we'll get a couple of days to practice and work on memorizing those formulas. All right. All right, your homework, just page 19. Okay, so just page 19. I'll send out a reminder this afternoon, and then link to the key as well.
I want to think about
Are you serious?
Thank you.
Yeah.
Yeah.
But it's like.
What? Yeah, I know.
Have a great day, guys. See you tomorrow.
Wait, I have
Too, buddy. But she looks like she like got money on the phone. Like 5. So, is it right? I think like this person, I'm like.
I agree. Don't be transferring names. What? I was about to say, it seems like people.
No. The doctor.
Okay, I was really for it. That was okay. This is fine.
I did take it.
Yeah, I don't believe that though.
Actually, okay. You can lock in on one. I don't know. That is. It's not even. You got it. It's not work. I spent like 20 minutes, but I'm not gonna go sit back. Yeah. So you know, those what?
Yeah, thanks.